In this video, we're going to compare the architectural level of abstraction with the object-oriented programming level of abstraction, C++ code on the left, with the algorithmic level of abstraction of how the Fibonacci recursive sequence works. What you're going to see in this video is in the middle, the recursive trace that you would probably want to draw up while working on code or taking an exam problem, to be able to see what it is that you're doing as you go through the recursive trace. First, when we reach main, we've allocated code on the stack, and we have the stack pointer in main. Next, I want to make the Fibonacci call. I am passing the value 5 here, and it's going into. Now what's going to happen is, when I actually go here into this code, I'm first going to check to see if n is equal to 0 or if n is equal to 1. Then when I get to this line of code, the important thing that will help you visualize recursion is that I have to do both pieces of code, which means I need to make both calls. In order to be able to see this, I draw out F4 and F3. But before you can get to this piece of code, you have to completely execute this piece of code, which is actually putting another copy of this recursive call onto the stack. So right now we haven't actually created a copy on the stack because we have not actually reached this code. So now what's going to happen is 4 is going to get to the top. It's not going to be equal to 0 or 1. And so now we're setting up again for 3 and 2. But again, we see that we have to go this way first before we even get to these calls. So this is why a stack and drawing it out is important, so you can visualize how it's going. So we're going to do the same thing with F3, do F2, and now we're at F1. So we get here, and now we see that n is equal to 1. What you're going to see over here is I have allocated registers for the returns. I've drawn it out this way for simplicity for the animation, but we see how we have what we're passing and all the return values and how it's going to be propagated out. So when we get here, we're going to see that we're going to return the value 1, and now what's going to happen when we return, we're going to go back up to a function called 2. We're now going to see that we've completed this side, so now we're going to go to the right. And now we're going to make F0. What you will see on the instruction stack is fib2 is now going to have fib0 on top of it because we've cleared fib1 off of it. So we see that's why that's the case. Then we actually go to the fib call and we see that we have 0 set up. We go to n is equal to 0. We see that we're going to return 1, and then we do. What we're going to see now is the fib0 is going to be removed from the stack, and then what's going to happen here is we're going to see 1 plus 1, which actually represents 1 plus 1, which is going to be returned by fib2. We see that they're removed. We see the 1 plus 1 is set up, and now we're done with F2 there. Because we're done with that, we go back up to the calling function F3. What we're going to see here is that we did this, and just like before, we're now going to go to the other side. So now fib2 is going to be removed from the instruction stack, and now we're back at fib3. We see at the different levels of abstraction that here at the algorithmic level, I know I'm calling F3. At the object-oriented programming level, I am now calling the right-hand side. And at the architectural level, fib3 is where I'm currently pointing in the instruction stack. I do already have 2 returns because that's what's been returned from 2, and now I need to go this way. So now we're going to make that call, and now we're going to put a copy of fib with the value 1 onto the stack. We go through here and we see the values 1. When we return, we're going to pass that value up, and now we're going to have 2 plus 1 is going to be in fib3, which is what we see here. Fib2 gave us 2, fib1 gave us 1, and now this value is going to return 3 to the function f4. So now we're going to go to fib4, we're going back up, and again, we have finished off f3, so now we have to go to this call. So now we're going to go this way, and as I mentioned in the reading, you're going to start to see that we're going to do a lot of redundant work. F2 is going to have F1 and F0. We've also already calculated Fibonacci 2, but here we have to go through this whole process again. You see we go through the whole thing, and now we have 3 plus 2, and we're here. Note how we've already done F3, but because of the way we have this set up, we're going to have to go through the entire trace again. So let's go through. We're now up to the solution, but we've only done this half, right? So here we are at fib 5. We've only done this half, which means we have to make the fib call N2, which means we have to make this call here. And that means we're going to go through the same process. I'm going to go through it a little faster in the interest of time, but you're going to see the same pattern as before. We're back up, and now we've gone through all this work that we've already done, and now we're at fib 3. We're going to return 2 plus 1, just like we did previously with fib 3. And now what's going to happen is it returns 3. We're now up to the last call. The left-hand side returned 5, the right-hand side returned 3, and now we return that value to main, which is why we're going to return 8. So there are some issues here. Skip that. All right, so here is the entire trace we just went through. And now we're going to go through and see precisely how much redundant work we did. Here to get fib 0 and fib 1, we make 1 call. For 2, we got to make 3 calls. For fib 3, we have to make 5 calls. For fib 4, we got to make 9. For fib 5, we need to make 15. And if I do 6, we have to do 25, which means we have to make fib n minus 1 plus fib minus 2 plus 1 calls. And that gets expensive really quick. And this is the same table that I have in the rating, but you see that with 10, I'm making 177 recursive calls. Now, if I go here and I run make clean and then clear, and I run make fib, now if I run fib 5, we're going to see that we get 8 as we expect. If I run 10, to the naked eye, it looks like it runs about the same. But now let's do 25. Still comes back pretty fast. So let's do 35. And did you see that it hesitated a moment? It's because we have to make a crazy number of calls. If I go to 40, it's going to take a moment to do all the calculations. You see it gets exponential. If I do 50, it's going to take even longer. And if I did 1,000, we see here at the bottom, it's 1.4066 times 10 to the 209 recursive calls. I could run this, press enter, and come back when your grandkids graduate from Notre Dame, and this might still not actually be solved. Plus, we don't have that space on the instruction stack, so you let it run long enough, you will get a stack overflow. So what we're going to visit in the next section, this idea of memoization, is how do we get around this problem?